So a lot of the work today is going to be like on the document camera. So I'm going to kind of like be back here. And so I printed out the do now so I can do it on the document camera so that way you guys can still see it. For number 1 on the do now, when we think about the type of problem that we have 2 equations with delta H values. And it says calculate the delta H for this new reaction. So we have 2 reactions up here. We have to find the delta H for a new one. This is Hess's law. So what we need to do is we need to figure out, there we go, how can we manipulate these 2 equations to get this new one? Now, when we look at manipulating equations, look for a unique formula. So CH3OH is pretty unique in terms of it's not in multiple equations. Notice how you have carbon in multiple equations, oxygen in multiple, sometimes you have hydrogen in multiple. So I'm going to look at CH3OH first. So I need 1 CH3OH as a product, just 1 mole. So if I look, I have the first equation and the second equation. Second equation has 2 moles of CH3OH as products. Well, I don't want 2, I only want 1. And so what would I need to do to this equation to only get 1 mole of CH3OH? Divide by 2. All right, and whether you say that you divide by 2 or you multiply by 1/2, either one works. So when I divide by 2, that's going to make this 1. It's going to make this 1/2. We'll make this 2 and make this 1. So I'll rewrite that equation down here so that we can see it. So carbon plus oxygen, 1/2 oxygen, plus 2H2 yields CH3OH. And that delta H is negative 201.2. So it's still the same sign because I didn't have to flip the equation. I just had to divide it by 2. So then we look at this top equation. I manipulated the bottom equation. So now we have to look at how we manipulate the top equation. Well, I don't see carbon or oxygen anywhere in here, so I'm going to focus on CO. I need 1 mole of CO as a reactant. So I need 1 mole of CO as a reactant. So I actually need to do 2 things to this top equation because I have 2 moles of CO as a product. What's one of the things I need to do to this top equation? Flip it. So if I flip it, I flip the sign. I'm going to flip the equation. And what's the other thing I need to do to make sure I just have 1 mole of CO? Divide that one by 2 as well. So that's going to give me 1, 1/2, and 1. So I'm going to rewrite this equation. CO yields carbon plus 1/2 O2. And so for that delta H, 221 divided by 2 is 110.5. That's going to be positive because I had to flip the reaction. So I've manipulated these 2 equations. I know I didn't line up the arrows here, but we can take a look at this. I have 1 carbon on the left, 1 carbon on the right. So I cancel before I add everything together. You could add everything together and have all of the reactants, the arrow, all of the products, and then cancel out everything that's the same. I just kind of do it beforehand. So I have 1 carbon on the left, 1 carbon on the right. Those will cancel. I have half of an oxygen on the left, half of an oxygen on the right. And there we go. So now when I add these together, I have CO and 2H2 on my reactant side. And I have CH3OH on my product side. So now I have the same reaction that the problem wanted. And so I added those two reactions together so I can add together their delta H values. So if I do negative 201.2 plus 110.5, negative 90.7 kilojoules. And there we go. And so that was using a Hess's law problem. You're manipulating the equations in order to get this new overall equation. So you always only use the equations that they give you and somehow manipulate them. Whatever you do to the equation, you have to do to delta H. So the second question, I'm going to zoom in on even more. This question was actually from the weekly review last week, which actually came from the quiz that we usually take within the next couple of days, but just with timing, we're just not going to take the quiz. So this says that a student dissolves NH4NO3 in water, and then it says we have the initial and final temperatures. They give us the close-up of the thermometers. What is the calculated delta T of the water reported to the appropriate number of sig figs? So everybody had the correct answer, just not to the correct number of significant figures. So when it comes to reading a thermometer, reading anything, a ruler, you measure what you know, and then you can estimate one place past that. So if I look at this initial thermometer, each one of these lines represents 1 degree Celsius. So if I zoom in even more, so that way you can see it up close, this large line represents 25. The water line is not exactly on 25, it's between 25 and 26. So all that we absolutely know is that it's at 25. You estimate one place past that. So I'm going to say that this is 25.5 degrees Celsius. You measure what you know and you estimate one place past that. The final temperature, if we look closely, the water line is exactly on the 20. So based on the graduations, right, each one of these is 1. So we know for sure that it's 20. If it's exactly on the line, then our estimation is just adding a 0.0. So we have our initial, we have our final. Now is where it gets into calculating delta T and remembering what we do with sig figs in math scenarios. So nothing changes about delta T. Delta T is still final minus initial. So final is 20.0. Initial is 25.5. When you add or subtract, you need to make sure that your answer has the same number of decimal places as your information with the least. So instead of least number of sig figs, it's least number of decimal places when you're adding and subtracting. So both of these just have 1 decimal place. Our answer should just have 1 decimal place. So it's actually negative 5.5 degrees Celsius. When you multiply and divide, that's sig figs. This was a multiple choice question on the test a couple of years ago. They don't often ask these, straightforward sig fig questions, but a couple years ago they did. So this is just remembering, 1, how to measure. So measure what you know, estimate one place past that. But then also remembering when you add or subtract, you're looking at least number of decimal places. And then when you multiply and divide, you're looking at sig figs. Most of our math is multiplying and dividing, which is why we always look at sig figs. So number 2 is just negative 5.5. Tomorrow's do now we'll look at, so this was one of the 2 most missed questions from the weekly review last week. The other one we will look at tomorrow in the do now. Okay, so that's it for the do now. What we're going to do now is we're going to actually switch to the lab. So you can put your do now sheets away. What you need out is your lab notebook and your lab handout. Okay, so what we're actually going to do is we're going to go through the pre-lab questions together. So you can double check your pre-lab questions and you can transfer them into your lab notebook if you haven't yet. And then we're also going to set up the data and observation section together because there are lots of data tables. So we'll actually set up the data and observation section together. This lab is not the most exciting in terms of collecting data. The biggest thing with this lab is all the calculations that we do after, which is why we're doing a lot of the calculations together. But for the lab, I had recorded it last week, I think. So we're going to actually you'll just get the data from the procedure video. So that's how we're going to do this lab. And then you'll have time to actually watch that procedure during class time today. So we're going to start with pre-lab questions. And so what I'll do is I will answer pre-lab questions in our lab notebook. So I didn't do purpose and procedure in here, but hopefully you have your purpose and your procedure already done. Purpose of the lab you can find in the experiment overview. So in the lab handout itself, there's always lots of really good information in the background. You get lots of equations that are going to be really useful. And then this experiment overview always has the purpose. You do not have to write the whole thing, only part of it. So you just paraphrase. So then I'll just start with the pre-lab questions. And remember, on the first page, you should have experiment number, the title of the experiment, and the date that you started, and at least your name. Since we're just watching the procedure, you don't have to put your lab partner. So, but you do need on the first page, experiment number, title, date, and your name. On every subsequent page, you can just put your name. Don't forget, before you turn it in, you should also always sign and date the bottom of every page. So just keep that in mind as well. So for the pre-lab questions, I'm looking at page 2 of the lab, so back of the first page. And there are actually 5 pre-lab questions. There are 4 on this page, and then there's 1 on the next page. We're going to go through each of them so you can make sure you have the correct answer with the pre-lab. So for number 1, it says define delta H of reaction. So delta H of reaction is the enthalpy. So we'll go ahead and we will just answer number 1. So remember, for pre-lab questions, you don't have to write the question out. You're just answering it. So number 1, delta H reaction. So delta, it means change in. So we'll say it's the change in enthalpy of a reaction. And in parentheses, I'm going to say heat absorbed or released. I'm just going to say kilojoules per mole, just kind of as a reminder. All right, it's measured in kilojoules per mole. So pre-lab question number 1, delta H reaction is the change in enthalpy, or it's the heat absorbed or released in a reaction measured in kilojoules per mole. Number 2, define specific heat. So 1 and 2 are just definitions. So 1 and 2 are just looking at definitions. For number 2, specific heat. So if we think about the units for specific heat, joules per gram degree Celsius, specific heat is the amount of heat, and in parentheses I'll put joules, required to raise 1 gram of a substance by 1 degree Celsius. Because your units for specific heat are joules per gram degree Celsius. And so specific heat is the amount of heat required to raise 1 gram by 1 degree Celsius. So 3, 4, and 5 is where we get into the math. So 3 and 4 are solution calorimetry questions, similar to what we looked at yesterday. So in number 3, it says the specific heat of a solution is 4.18 and its density is 1.02. The solution is formed by combining 25 milliliters of solution A with 25 milliliters of solution B, with each solution initially at 21.4 degrees Celsius. Final temperature is 25.3. Calculate the heat of reaction, assuming no heat loss to the calorimeter. Use correct sig figs. So this is a solution calorimetry problem. We know that it's solution calorimetry because it says we are mixing 2 solutions together. So in a solution calorimetry problem, we always have 2 focuses: Q reaction and Q solution. In number 3, it says assume no heat loss to the calorimeter. So that means we don't have to worry about Q cal. So Q reaction plus Q solution equals 0. It wants us to actually just calculate Q. So it says heat of reaction, but it says Q. So I'm going to solve for Q reaction. I don't have to worry about switching it to delta H. We're just solving for Q. So that means I'm going to leave Q reaction alone. Q solution I can plug variables in for. Q is MC delta T. So we'll have mass of solution, specific heat of solution, and delta T equals 0. So over here off to the side, I'm just going to show some of these calculations. Mass of the solution. Like yesterday, when you mix 2 solutions together, you have to use the density to go between the volume and the mass. In this problem, we are combining 25 milliliters with 25 milliliters. So we have 50 milliliters total of solution. That's just from the problem. I added solution A to solution B. Now it's not just the density of water. It's not just 1 gram per milliliter. It's a little bit different. So I'm going to use the density as a conversion factor. Density lets me convert between grams and milliliters. So I want milliliters on the bottom so that it cancels. I want to go to grams. Density, in this case, is 1.02 grams for every 1 milliliter. So 50 times 1.02 is 51 grams. That's our mass of solution. So Q reaction is what I'm solving for. Mass of solution, 51 grams. It says that the specific heat of the solution is 4.18 joules per gram degree Celsius. And then delta T, I'm going to put over here. You don't have to show the delta T calculation. I'm just showing it so that way we remember. Delta T is always final minus initial. And so final was 25.3. Initial was 21.4. 3.9. There's our delta T, 3.9 degrees Celsius. So here we're calculating Q solution. So I'm going to do 51 times 4.18 times 3.9, 831.402. So based on our given information, I'm going to use 831 joules equals 0. So then to calculate Q reaction, we just move it to the other side. Negative 831 joules. Right, if you did negative 830 for 2 sig figs, that's fine as well. So this is using the idea of Q reaction plus Q solution equals 0, plugging everything in. Now number 4 is just slightly different. So I'm going to move this up so we can still see number 3. Pre-lab question number 4 says, in question 3 above, the calorimeter has a heat capacity of 8.2 joules per degree Celsius. If a correction is included for the heat absorbed by the calorimeter, what is the heat of reaction? So now the problem is telling me, instead of just Q reaction plus Q solution equals 0, we're going to have Q reaction plus Q solution plus Q cal equals 0. Now we look at this and we're like, oh man, we're going to have to do all that work again. But we actually aren't. We know that, again, we're solving for Q reaction. We just calculated Q solution right here. We did MC delta T of the solution. We know what that answer is. MC delta T of the solution is 831 joules. We just have to calculate Q cal. Remember that Q cal is C cal delta T. So again, if we solve for Q reaction, Q solution we've already solved for. C cal, it tells us in the problem, is 8.20 joules per degree Celsius. Delta T is always the same. Whatever the delta T is for the solution is also the delta T of the calorimeter. So 8.2 times 3.9. This is 31.98 joules. All right, when I multiply these two together, that's 31.98 plus 831. So if I keep it to 3 sig figs, 862.98 is going to round to 863. So Q reaction plus 863 joules equals 0. So now Q reaction is negative 863 joules. So number 4 is actually more like what the example was yesterday that we looked at. In yesterday's example, we had reaction, solution, and calorimeter. So if the calorimeter does actually absorb some heat, the reaction will release 863 joules. Okay, so then we have one more question, so I'll be able to fit it right down at the bottom. Pre-lab question number 5 says, if the reaction in question 3 is A plus B yields AB, and molarity of A is 0.6, molarity of B is 0.6, calculate the enthalpy of reaction, so delta H, for the formation of 1 mole of AB. So now what we want is we want kilojoules per mole of AB. That's what this is asking for. Kilojoules per mole of AB. Now something to think about. The molarity of A and B is the same. The volume of each solution was the same. It was 25 milliliters of each. Since molarity and volume is the same, moles are the same. So something I'm just going to write down first is that moles of A equals moles of B. That means there's no limiting reactant. Makes it very nice for us. And based on the balanced equation, it's 1 to 1 to 1. That means whatever the moles of A and the moles of B are is also the moles of AB. So that's going to be useful because if I find the moles of solution A or the moles of solution B, that's the same as the AB solution. So that's going to make it easy to find moles. So here's what I'm going to do. I'm going to remember that molarity is moles over liters. Molarity is moles over liters. It doesn't matter which solution I pick. They're the same. Both of them had a molarity of 0.60 molar. That's X moles. And we need liters. If you look back at question 3, it was 25 milliliters of each. So just a quick reminder down here that 25 milliliters is 0.025 liters. If you remember that, you don't have to write that down. I'm just writing as much down as I can just to help us remember. It has to be in liters to plug it in. So 0.025 liters. So if I multiply these two, 0.6 times 0.025, 0.015. So it's 0.015 moles of A and B and AB because it's a 1 to 1 to 1 ratio. So now it wants kilojoules per mole. That's what delta H is. So I'm going to take my Q. I'm going to take my Q and I'm going to put it in kilojoules first. 863 joules is how many kilojoules? Divided by 1,000. All right, so 863 divided by 1,000 is 0.863. All right, 0.863. So Q reaction is negative 0.863 kilojoules. I just put it in kilojoules first just to make it a little bit easier. If you're not familiar, you don't remember the conversion, 1,000 joules is 1 kilojoule. So here's Q. If I divide by moles, that puts it from Q to delta H. So if I do negative 0.863 divided by 0.015, delta H of reaction now becomes negative 57.5 kilojoules per mole. So to go from Q to delta H always wants kilojoules per mole. So delta H is always going to want kilojoules per mole. And to do that, we take our Q, which is in joules, convert to kilojoules, so divide it by 1,000, and then we divide by moles. What we looked at last week is we always had grams on the bottom because they gave us grams. And then we just converted using molar mass. we did that mole conversion. We just kind of did it off to the side at the same time. So these were the pre-lab questions. You could double check your answers. If you have to fix any of them, you can. But I wanted to make sure that we went through them. These are very similar to the calculations that we're going to look at tomorrow and Thursday. So any questions on pre-lab? Let's see. I don't see any for them either. Okay. So the next thing that we're going to do before you guys collect data is we're going to actually set up the data and observation section, because I want to make sure that you're labeling everything appropriately so that way you're not missing any points for formatting. So I finished pre-lab questions on this one page. So I'll go to the next page for data and observations. Now, if you do your data and observations down the side, that's fine. You can just fit everything like on one side. You'll be fine. The biggest thing with this lab, if you look at the data and observations section, which starts on page 5, I tried to include lots of information, kind of like off to the side. You'll notice here what I did is I started labeling the data tables. This has 1, 2, 3, 4 data tables in it. Every data table needs a number and a title. So like this, data table 1, part 1. Down here, data table 2, part 2, reaction 1. Your next one would be data table 3, part 2, reaction 2. So I want to go through and just kind of look at how this would look. I'm going to work all the way across on the page. If you do your data and observations down this one column, then you just work down one column and flip the page when you need to. So all of your temperatures, data tables, always go in your data and observations section. Okay, everything always goes in your data and observations section. Now we're going to be doing a lot of data tables, so if you need a ruler, you can come up and grab a ruler. If you're like, I can draw straight on the lines, then that's fine too. I'm going to use a ruler because even when I try to draw on straight lines, they're not very straight. So if at any point you think you need a ruler, you can just come up. They're right up here on the front table. So for the data and observations, we're essentially going to take what is in the handout and transfer it to the lab. So I know it says part 1 data table, but we're just going to label it part 1 because we'll label all of our data tables appropriately. So I'm going to start by labeling this part 1, determination of heat capacity. Again, if you're going down one column, keep going down one column. That's fine. I'm just working across. We are just going to transfer what we see over. So the first thing is initial temperature. So initial temperature. And then we have 50 milliliters H2O at room temp. I'll put a line. 50 milliliters of H2O heated. I'll put a line. And I'm paraphrasing some of it too, condensing some things together. But this is where we are going to put all of our data and observations. We have to make it really easy to find everything because we're going to be using a lot of this information in the calculations. So then it comes to the first data table. So it says mixing data, but you're going to notice I labeled this for us, data table 1, part 1. So 1, 2, 3, 4 columns. And if instead of making 4 columns, you just put it all in like 2 columns, so you just do all the time and all the temperature, that's fine. You just need to make sure you have like from 20 seconds to 180 seconds. 1, 2, 3, 4, 5, 6. Okay. So now I'm going to start by labeling this data table. So data table 1, part 1. Every single data table needs a number and a title. When I say number, I mean it needs to say data table 1 or data table 2, and then you give it a title as well. So I'm going to use a ruler because I can't draw lines very straight. I'm probably making my data table way bigger than it needs to be, but it's okay. So time in seconds. Temperature in degrees Celsius. Yeah, this will be fine. Time in seconds. And temperature in degrees Celsius. Also, mine's not going to be as even probably as it should be. 1, 2, 3, 4, 5, 6. Okay. All the way across and down. All right, so then I can go through, I can draw my other lines. Is it going to be even? Probably not in terms of like number of boxes, but I'm not picky about that. And if you actually, instead of like putting lines, you know, for every single time, you could just do like this. As long as it looks neat, you're okay. The point of using a ruler is just to make the data table itself look neat. 160. Oh yeah, that would bother me. I didn't do it on this line. Oh well. All right, so then you have your data table. And the data table will get filled in while you watch the lab. It's really not an exciting lab. We're not really missing out on much by not doing it in person. It's part 1 is mixing hot and cold water together. Very exciting. And part 2 is mixing 2 clear solutions together and recording the temperature every 20 seconds. Also riveting. It's the calculations that are the most important for this lab. The specific heat of a metal lab was the better one to do in person, and unfortunately we didn't get to. So there's data table 1, part 1. And then if you notice underneath the data table, we have 2 temperatures, Q and C. So I'm going to just go ahead, I'm going to actually just list them straight across. So T mix, degrees Celsius, put a blank. T average, degrees Celsius, put a blank. Q cal in joules, blank. And C cal, blank. Also, didn't think about how far I was drawing the lines, but again, that's okay. Our data and observation section is going to be very thorough for this lab. So that's just part 1. And if it helps to kind of put like a star for part 1, that way it's easy to find part 1. And then we want to put a star, part 2, determination of heats of reaction. Then we'll go through. Notice for part 2, show you this really quick. For part 2, it says reaction 1 gives us all of the information. Reaction 2, right up here, gives us all the information. Reaction 3 gives us all the information. We do want to split it and make sure that we can tell from each reaction. So I'll start by putting reaction 1. And I'll write out the reaction just in case we need it. And NaCl, H2O. Then we'll go through just like before and we'll put initial temperature, we'll draw our data table, and then we'll include the variables at the bottom. So initial temp, 50 milliliters, 2 molar HCl, put a blank. 50 milliliters, 2 molar NaOH, put a blank. And then it comes time for another data table. The data table is the exact same as the first data table. All the data tables are going to look just like this, except it's a different number and a different title. So let's see if I can draw this one a little bit better. I'll label it first. Notice I actually tried to label it for you in the lab. Data table 2, part 2, reaction 1. So data table number 2 is the data for part 2, reaction 1. So see if I can draw this straight. And then 1, 2, 3, 4, 5. Oh, perfect. Okay, mine's going to go all the way to the bottom of my page. So I'm just drawing the outline of my data table. You have the option of drawing the outline like this or drawing a line for each part of the data table. That's your preference. So I'm going to do this. All right, so I'm going to have my heading at the top. So I'll have time and temp. 1, 2, 3, 4, 5, 6. Time and temp. All right, so then that's our second data table. And then you're going to do the same thing for reaction 2 and reaction 3. The only difference is that you'll have data table 3, part 2, reaction 2, and data table 4, part 2, reaction 3. So 20, 40, 60, 80, 100,
Miss Mama told me
40, 160, 180. So there's reaction 1 of part 2. And then for most people, they'll have a page that looks just like this, except you'll have reaction 2 at the top, reaction 3 at the bottom. So we did the first two together. So then for reaction 2, you want to make sure that you label this so we're ready for data table 3. So this would be data table 3, part 2, reaction 2. And then down here, data table 4, part 2, reaction 3. Oh, I forgot to put the numbers at the bottom. All right, we have these 3 values down here. Oh, nuts, I'm out of space. I'll just do it over here. So we'll have T mix in degrees Celsius, T reaction in joules. So like these numbers, I would put underneath the data table like I did these up here. I just ran out of space. And then we'll have delta H in kilojoules per mole. So again, these three numbers would go underneath my data table. If I would have moved this up one, I would have had space. And so then, again, you'll have data table 3 with your title, data table 4 with your title, and then that will get drawn in your data and observations as well. So and I know the bell's going to ring in a few minutes, but I do want to, let me go to the window so that everyone can see it. Did I close out of it? Oh, I know why. There we go. So for the rest of class, the lab itself is, I think it's like a 15-minute video. It's in YouTube, so you can like speed it up. If you want to watch it on 2 times speed, get it done in 8 minutes, you can. The link is in Google Classroom, but I also put like a short link up here. So I'll keep this up on the board. So you'll watch the procedure and you'll collect your data and observations. So your data and observations are going to be the temperatures and filling in the data table. Some of the variables like Q, delta H, those will be calculated in the calculations section. So if you're not filling something in, don't worry about it because we'll probably fill it in tomorrow and Thursday when we do the calculations. So I have the link for the procedure video. So if you want to just type it in, you can. If you want to go to Google Classroom, if you click on the Thermodynamics lab, the video is there as well. But it's in YouTube, so you can speed it up, slow it down, however you want to watch it. All calculations we will do together tomorrow and Thursday. I know you guys are at home tomorrow, but we'll have the calculations. Like I'll be doing them on the board. And so, you know, we'll be able to make sure that everyone has the calculations. Make sure, and you'll be on your Chromebook on Google Meet, but we'll have to like dual screen because we're going to be using Google Sheets a little bit too. So we'll take our time with that, but there's some graphing. Once you finish the procedure and you have everything written in your data and observations, you can work on mastering. So you'll have some time because it's not going to take an entire period to watch everything. So you can wait until you come back like after the break, but then you'll have some time to watch the procedure, fill in data and observations and all of that.